Hello, good evening, everyone. My name is Yvette. Greetings from Malaysia. Wherever you are joining us from, wherever part of the world you're joining us from today, I hope that your day has been splendid so far. It is 5 p.m. here in Malaysia, and welcome to our session. Today, we have a very informative session for you, organized by the Southeast Asian Region IMechE and hosted by Asia Pacific University of Innovation and Technology, Malaysia. That's where I am right now, and I hope that you enjoy this session today. Today's session will be by Mr. Matthew Laskaj. Matthew is the current chair for the Institution of Mechanical Engineers Scottish Region and is the current director of a very successful engineering consultancy and training business. Starting his career in Australia and having worked throughout the world in manufacturing plants, refineries, and offshore oil rigs, Matthew now lives in Aberdeen, Scotland, and loves to help engineers all over the world develop their skills and improve their business. So without further ado, let me leave you in the capable hands of Matthew to speak to you about how to improve your maintenance strategy. Matthew, on to you.
Terima kasih, Yvette. Selamat datang kepada semua.
That's good.
I learned Indonesian about 25 years ago. My accent was terrible back then, and I'm sure it's gotten worse now. So I promise you the rest of this is going to be in English.
I'm glad for that. We are all glad for that.
All right. Thanks very much. Thank you for everybody for joining in. As Yvette said, my name's Matthew Laskaj, and it's awesome to be here and to have so many people joining in from not just Asia, but all over the world potentially. So please feel free to leave your comments in the chat box throughout the session. Where are you calling in from, listening in from, and also what questions you've got throughout the session. So I won't be able to see the chat necessarily throughout the session, but Yvette's going to monitor it for us, and we'll have an open question and answer session at the end that we can all talk about then. So keep the questions coming. So what I'm going to do is I'm going to share my slides now, and we can get started. Righto. So today we're going to talk about the importance of maintenance. And we all know that a key to business success is having a good maintenance program or a good reliability program or good strategy. Maybe you struggle with a few areas though. Maybe it's getting the business case that management will support so you can get your strategy set up in your business. Maybe it's actually understanding how productive you are as a business or how reliable your equipment actually is. What I often find is people just don't know where to start. Starting can be the hardest part, so hopefully today's session I'm going to help you out with some of those things. The whole basis behind improving maintenance and reliability is you want to improve safety and increase profits, because if you're not increasing your profit, you don't have a business. You want to reduce your maintenance and production costs and also reduce your inventory. So the more equipment you've got sitting there, the more it's costing you. So cost is a big driver of improving your maintenance. You want to improve stability and predictability of your equipment, because you want to know when you think it's going to fail or when you have to have the work done. You don't want to be caught short and not know when something's going to happen. So we want to extend the equipment life. Of course, we all want less stress in our life. Overtime, unplanned work makes more stress. So improve your strategy and it will reduce your stress. And by getting a sense of employee ownership, it's important that the workers feel like they're part of the team, feel like the equipment is theirs. So there's two key areas I want to focus on. What are the building blocks or the fundamentals of maintenance plans and maintenance strategy? And then how do you use that knowledge to build your own plan? So throughout the next 45 minutes, I want you to have a think about this question here. What are 3 steps or 3 pieces of information that you get out of today's seminar that will help you master your own maintenance and reliability plan? I'm going to give you my 3 at the end, but I want you to think about what are the main 3 things that you take away from today that you can actually put into your own maintenance plan. So first, have a think about the place where you might work or somewhere you've worked in the past. Something breaks down. And for whatever reason, it's quite often on a Friday night or a weekend or sometime when you don't want it to happen. All of a sudden, you've got a breakdown. Production's on your back to get it fixed. We need to get production out the door. We're losing money. Get it fixed. Quick, quick, quick. So the maintenance team do a really temporary fix, what we call a Band-Aid fix. They put a plaster over it. Fix it quickly, get it up and running as quickly as possible. So that makes them stressed. They're overworked because things happen at the wrong times and they're stressed trying to get it fixed quickly. That means that the standards drop. They don't do work as well as what they could if they had more time and they were planned better. And maintenance then gets missed out because you're spending all your time on the reactive maintenance rather than the planned maintenance. This means our backlog grows. Our planned maintenance backlog gets worse, which starts our cycle again, because if we don't do the planned maintenance, we get more breakdowns. What do we do about it? How do we get out of this crazy cycle of this reactive stress running around with pressures? You've got it. The whole point of today's presentation is we need to improve our maintenance plan. By having a good maintenance plan and the right strategy, we will help with this. Let's look at it another way. In my experience working in manufacturing and refineries and offshore oil rigs and things, a maintenance manager's usually in place for about 2 years. They first come in and what do they want to do? They want to look great. They want to do a great job. So let's cut costs. That'll make me look better. Well, we can't cut production costs because that makes us money. So let's cut maintenance costs because that's not making us money. In fact, no one's probably going to notice for a while. So they cut the spending. 2 years later, they're looking really good. Costs are down. Failures haven't increased. Stresses are reduced. Less worries about it. So they get promoted. Then the next person comes in, and it's usually the supervisor. All of a sudden, things start to break down. Now we're back into this reactive cycle where we've got stresses, production pressures, all sorts of problems going. What do you do to fix it? How do you catch up? Because the last person's cut costs, you can't ask for more money. Same answer, by having a good maintenance strategy. This is a quote from about 5 years ago. I said at the moment I live in Aberdeen and I work a lot with offshore oil rigs and very critical assets. Industry as a whole is performing well. However, oil and gas is a major hazard sector, obviously. What they found in 2015 was that safety critical maintenance offshore was getting a backlog in their planned maintenance because of, at the time, the oil price dropped, so people got cut from their jobs, less people. So less work was getting done. Does this sound familiar? The last year, COVID has affected us in exactly the same way. We've been able to send less people out to refineries and manufacturing plants and offshore oil rigs in particular because we can't get offshore. So the safety critical maintenance gets reduced. Is that a problem? How do we make sure that our equipment is maintained safely when we've got cost pressures, time pressures, staff pressures? The answer is to have a good management system. We need to assess the risk, make sure that the right people are involved and talked to, so technical people, engineering people, but don't forget the actual engineers, maintenance and operators on the shop floor. Okay, so good strategy, assess the risk, involve the right people, make the decisions. we can absolutely defer critical assets as long as we make sure that we do it in the right way. So on to how we improve our maintenance plan, the whole point of today's topic. The goal of maintenance, in my opinion, is to keep production running in good working order at as low a cost as possible. So we want to keep it doing what we want it to do, but without spending too much money. There's two parts that go into that. There's the technical actions, so the person on the tools, the person doing the physical work. And then there's all the administrative actions that go along with that. The paperwork, the planning, the scheduling, recording of failures, recording of work done. Those two go together to help us achieve our aim of retaining the item or restoring the item back to that state that it can perform its function. In other words, back to the point where it does what we want it to do as cheap as possible. There's a really good definition by a well-known reliability expert named John Mowbray. And he says that maintenance and reliability is ensuring that the physical asset continues to do what the user wants them to do. So you need to decide what is it you want your asset to do. Make sure your maintenance plan helps it continue to do that as low as possible. So let's go back a little bit. Think about the early 1900s. What did equipment and manufacturing and plants look like back then? They were slow moving. They were really over-designed, over-engineered, didn't fail very much. There wasn't a lot of pressure on manufacturing and production to get products out, so life was pretty easy. If something broke down, no problem, let's just go out and fix it. If it's not broken, don't fix it. Then everything changed. World War II came along. All of a sudden, the pressures skyrocketed. Companies like Ford went from making cars to making military equipment and munitions. What happens if you don't get equipment out the door quickly now? What happens if your designs and equipment fail? People end up dying. So the consequences rose, so the pressure rose. So now we can't just wait for things to break down. We need to try to make sure it doesn't break down in the first place. So we've moved to this overhaul understanding, this make sure that we overhaul it or remove it or replace it before it breaks down. Then as we moved on, our thinking got a little bit more advanced, and we thought, well, why are we replacing it if it may not need replacing? Let's monitor the condition. Let's do some kind of inspection or listening or feeling to see what the condition's like. If we think something's wrong with it, now replace it. Sounds more logical, doesn't it? Don't replace it if you don't need to. As our risk and environmental and safety priorities have changed over the last 20, 30 years due to some big incidents in particular, we're now trying to be more proactive. We're trying to base it on risk and condition and what we think is the best scenario. What's the consequence of the failure? How do we manage that? So our thinking of maintenance has evolved over the last 100 years from only fix it when it breaks to let's try to be more proactive. But it can still be any of those options. So really we have a choice of options as a maintenance professional to choose from. We can choose a reactive breakdown, run to failure option. We can do a preventive, planned maintenance. We can try to be more predictive, trying to do some condition monitoring. Something called total productive maintenance, which Toyota was particularly instrumental in getting involved in and developing. Then we look at some of the more risk-based things, so reliability-centered maintenance and risk-based maintenance. So what I want to do is go over some of these just to give you a bit of an idea of what are our choices of maintenance and engineering and reliability people to choose from. So what I've done is I saw this from somebody a while ago. Is the car is to try to represent the era where this thinking was and try to put some picture to the concept. So that's why we look at reactive or breakdown maintenance. We've got a pretty old car there. Luckily, that's not my car, but I've got a couple that are sitting there that aren't too far from it. So reactive maintenance, something breaks down, we fix it. We can see that the failure's occurred. So the idea is to bring it back to the condition that we need it to be running in. We can call it a corrective maintenance or breakdown maintenance, or more often I call it run to failure. We run it until it fails. Identify the fault, isolate the fault, fix the fault. Pretty simple. The next one's planned or preventive maintenance. We want to try to reduce the number of breakdowns by doing some interval-based work. Daily, monthly, 6 monthly, yearly. We do some work before that equipment breaks down. It can include visual checks, changing oils, changing filters. Think about your car. You go and put your car in for a service once a year. The idea is to try to stop breaking down by changing oil and spark plugs and filters and things. We can overhaul it, so we might rebuild the engine if we think that it's getting old. Or we might throw out the car altogether and buy a new car before the car fails, because the purpose of the car is to get us from A to B. So let's put that, as an engineer, let's put that into a nice graph. So on the left here, we've got the probability of failure. As time goes along, or as we move along the x-axis there, we've got some small chance of failure. There's always some little chance that we're going to fail. It then hits this dotted line, this magical dotted line, where it starts to all of a sudden wear out. Now, it might be gradual over its life, or it might be a sudden starting to wear out. And as that wear out gets increased, our chance of failure increases massively. So what we want to do is we want to try to pick that point where the dotted line sits and do our preventive maintenance at or before that point, because anything after it, we're increasing the chance of failure. Okay, so that's why every 12 months we change the oil on our car, because the life of oil is about 12 months depending on how much we use it. After 12 months, it starts to deteriorate and there's a chance that we're going to fail some other components. So we change it at 12 months. But there's some big assumptions that we make when we're doing this. The first one is that the equipment that we're maintaining follows this profile, that it's pretty low chance of failure throughout its life, and then it starts to wear out. Failure statistics are available. It assumes that we actually have good information to build our graph, and that our equipment is average. If I have two pumps sitting in the same building, 1 week on, 1 week off, rotating, I'll guarantee you that they will not fail on the same week. Even though the equipment's the same, the conditions are the same, the fluids and the process are the same, because not every equipment is average. Now what happens if I've got one pump inside and one pump outside? That's even worse. So we're making some big assumptions when we're using planned maintenance. How likely is the equipment that you have going to follow this information? So is planned maintenance the best option? Have a think about that. So I want to tell you a story. So let's go back to the 1960s. 1960s, the airline industries were starting to boom. And the aeroplanes weren't as reliable as they could have been or should have been. So United Airlines thought, I want to improve the reliability of my aeroplanes. How do we do it? If something's unreliable in your plant, what do you do? If something breaks down, what do? We do more maintenance, right? We schedule in more overhauls, more inspections, more changeouts. So it's exactly what they did. They did more work. They put redundancy in. They made things heavier. They put 2, 3 versions of backups in. Solved, right? No, it was not. They actually found that not only did it not improve, but some parts got worse. How's that possible? We do more maintenance, we put more backups in, it gets worse. So they hired 2 people to come and do a study. And what they found was that all of the equipment in the airlines followed one of 6 failure profiles. A, the top one in the left there, is the one I just went through, the classical failure profile. As life goes along, it's quite random throughout, small chance of failure, and it then increases as it gets longer into its life. B, pretty unreliable right at the start of its life, pretty good throughout its life, and then higher probability at the end. C, it just gets higher chance of failure the longer you go. D, pretty good at the start, not so good throughout its life. E, random throughout. So almost think about a light bulb for this one. You could turn the light bulb on the first day and it doesn't work. It could run for 2 years and then fail. You just really don't know when it is, and there's not much warning sign. And F, pretty good at the start of its life, pretty bad at the start of its life, and then random throughout. So what I'd like you to do is, in the chat box, if you're on YouTube, or if you're on Facebook, or if you're logging in another way, what one out of those 6 options do you think did they find the most? So if everyone wants to just stick something in the chat there, A, B, C, D, E, or F, which one do you think that they found was most common? Right, we've got one. First one from an I is F. Anas, going for G. Got an A, got a couple more Fs. D's, A's. All right, we've got a pretty good spread of ones coming in on the live stream there. Anyone on the YouTube? Just check the YouTube stream. I've got a couple coming in on YouTube as well. Excellent. Thanks, Daisy. Shah, D all the way. That's a pretty confident call out, Shah. So what I'm going to do, I'm going to share the results, and the results may surprise you. A, 2%. 2% of failures followed that classical failure profile that I showed you. 4% is B. 5% is C. If we add all of those together, only a total of 11% of failures occurred or followed what we call age-related profiles, where it's pretty good throughout its life or pretty random throughout its life, and it gets to this wear-out zone towards the end. Not just airline industries. The Navy did this study on submarines. Slightly different profile because the risk of submarines is much more than manufacturing, for instance, but pretty close. 68% F. So if you chose F, so Daisy there, well done. A few others chose F as well. I'll give you a gold star later and you can stick it on your fridge and show how clever you are. 68% chose of profiles followed what we call an infant mortality profile. Right at the start of its life is the highest chance of failure. Once we get into that a couple of time periods later, it's more or less random and lower. 89% random failures if we add all of these up. And again, it's not just the airline industries. The Navy was pretty similar. Manufacturing, pretty similar. So 11% of failures occur in this age-related profile, 89% random. 2 really important discoveries came out of this study from the airlines. The first one is, because most failures were random, by doing a scheduled overhaul, it really doesn't help much because you don't know when it's going to fail. So when do you schedule it in? There is a lot of items where there is no effective form of scheduled maintenance. If you don't know when it's going to fail, how do you know when to do the maintenance? If I maintain it today, could it fail tomorrow? If I maintain it today, I'm introducing a higher likelihood of failure tomorrow because of that infant mortality curve. So most times, equipment doesn't reach the end of its life because it gets changed out because something else causes us to change it. Avoid any unneeded maintenance. Do not do maintenance unless you have a good reason for it. Just because things are failing, don't default to doing more maintenance without thinking about it first, because we increase the chance of failure back to the start of its life. We could install it wrong. We could have stored it wrong. We could have transported it wrong. We could have used the wrong equipment. It might not fit. There's a whole lot of reasons why it's there. Monitor the condition as much as possible to detect when the failure is going to come, and then use your engineering understanding to decide when it's going to be changed. Asset management, or in particular ISO 55001, it tells us what we should do. It gives us a good understanding of what we need to do to develop a good strategy, but it doesn't tell us how to do it. We need to know how we can do it by designing better, buying and storing better, installing better, operating and maintaining better. These are the things we need to improve the reliability. So I spoke about condition monitoring and prevention as much as possible. So this is what we call predictive maintenance. Condition monitoring sort of forms part of that predictive maintenance. It can include visual inspections. So just looking at the condition, walking around, doing a walkthrough once a day, once a week. We can do some vibration analysis with some probes. We can do some ultrasonic testing, UT testing to check thickness. Check the oil condition. What's the oil like? What does oil tell us? We can check it with infrared, so thermography. We can do some non-destructive testing. There's a whole lot of different ways where we can check the condition, so we're not changing things for the sake of changing them. But the most important thing that, in my experience, is to get the operators and the maintenance teams involved. It's what we call operator care. They work on the equipment every day. They know what's good, what's bad, what doesn't sound right. They can monitor the processes just by doing their normal jobs. They can check equipment condition because they know what's not right. If you drive your car, you'll know that something's not right. You take it to a mechanic, will they be able to tell the same thing because they've never seen your car before? Look, listen, feel, smell. You can detect a huge proportion of things without fancy technologies, fancy equipment. But make sure that you have it planned into your strategy. So proactive maintenance, let's get a bit more proactive than even preventing a failure. So preventive maintenance is trying to detect when a failure has occurred, and we know that we then need to change it. Why don't we try to just eliminate the failure in the first place so we don't even have to do the maintenance at all? So this is where we're looking at eliminating defects. We can use root cause analysis, root cause based maintenance. We try to find what is the real reason the equipment is failing. Now let's eliminate the defect. Let's make it last longer by stopping it failing in the first place. Remember I said before that a lot of traditional maintenance, so reactive and planned maintenance, achieves nothing. And some actually makes it worse. So by looking at proactive ways, we're not going to waste our time doing maintenance that does nothing or makes it worse. Have good processes, good design. And it doesn't start when you start the on button, it starts when you're designing the equipment. Install it, start up, commissioning, shut down, good operation, good training is critical to having a good maintenance plan. And that's where what we call total productive maintenance comes into it. Okay, this started in Toyota in the 70s and 80s, became big. The focus here is on no waste, lean manufacturing. No waste, no defects, no breakdowns, don't run slow, don't stop, and more importantly, no accidents. Okay, so this is zero defect philosophy. And it's sort of centered around these 8 pillars. 5S is in the middle. For any bonus points, can anyone name what any of the 5 S's are in the chat box? If you can type in, if you can remember, if you've done it before, what are any of the 5 S's for those people out there who have not seen what 5 S's are before? As you're doing that, the 8 pillars, autonomous maintenance, making sure the operators are doing what they need to do to help out. Planned maintenance, good quality, focused improvement, training, health and safety, all of these things is what we're calling total productive maintenance, involving the people doing the work, the operators and the maintenance. Okay, so for those of you who are thinking about what 5 S's are, it's Japanese words. I'm going to, back to my accent here, I'm going to do the English versions of them instead of the Japanese versions. Sorting, shining, standardizing, all of these things which make us be able to detect that there's something wrong. If you keep your equipment and your workplace clean, you can see when there's a leak. You can see when there's something missing. Okay, so it's important to get the basics right. The thing that came out of the study from the United Airlines is what we call reliability-centered maintenance. It's a process, okay? It's not another technique. It's a process and a decision diagram that helps us make better decisions with the information we've got. It helps us determine what we need to do to make sure our asset continues to do what we want it to do in the current condition. Okay, so this is again from John Mowbray's definition of reliability. And it asks us 7 questions. Okay, it's a process map, process diagram. It asks us 7 questions. What is the function of the asset? What is it meant to do? How can it stop functioning in the way we want it to do? In what way can it fail? What causes that failure? What's a potential cause of that failure? What happens when that failure occurs? Safety, environmental, production. They're the 3 things that we care about when a failure occurs. All 3, then you're in real big trouble. What's the consequence of that failure? Does it cost us a lot of money? Do people get badly injured? Do we have an oil leak to the ocean? What can we do to prevent the failure from happening in the first place, or predict when the failure is going to occur so we can plan it in? If we can't do either of those, what else can we do? We might need to redesign it. I love a process map. I love pictures. So here's a map of how this would sort of work. Collect the information. And this is why plant maintenance doesn't always work so well. We don't have good information. We need to get better at collecting information. Failure history. How many times have we changed it? How much work have we done on it? How much does it cost? Then we work out the risk. Risk is consequence times probability. We then rank the risks from highest to lowest. Some criticality analysis. Based on the one that gives us the most pain, the most grief, we build in a plan using RCM if we really have high criticality, or maybe just using our engineering knowledge. The continuous improvement cycle, plan, do, check, act. We always have to keep evaluating, monitoring, and reassessing and improving. So we may need to go back and do that process over and over again. Okay, so this is what we call part of the risk-based process. For those of you who are involved in risk-based inspection, there's an API standard there, and it's mainly to do with thickness of pipes and thickness of pressure vessels. How long is fitness for service going to last? What is the risk? Okay, so if we can combine reliability-centered maintenance and risk-based inspection, we get what we call risk-based maintenance. So, all sounds good in theory, right? Very easy. We can set up some plans. We can look at our history. We can do root cause analysis. We can do all these fancy techniques and tools. But what does this look like in real life? It's going to take a lot of work to do. So how does that affect our end plan? If we're going to spend more money, think about our maintenance manager. The person you've just replaced has cut costs. They've done such a good job. They've been promoted. You've come in. How are you going to ask for more money? How are you going to improve the maintenance? So I worked in a edible oil refinery and packing plant, and we put in a new reliability program. So we revised, looked at every single piece of equipment in the entire plant with the aim of improving safety, improving predictability, efficiency, and of course profit. So how do we do it? We collect all the information, the planned maintenance information we've got in our computer, on walls, in people's heads, collect everything, break every single task down into individual tasks because quite often they're grouped together. Review what was done as a group. It's really important to get more people in the room than just me or you. If you get the maintenance technician, the fitter, the electrician, the operator, a supervisor, a manufacturer, all of these people in a room and say, right, here's a piece of equipment, go through the questions. How can it fail? What's the function? What's the consequence? What should we do to prevent or predict it? You're going to get a much better result than one person sitting there. So get a team involved. Put together new tasks. Review them. Put some plan in place so that they walk through the plant doing them in sequence, and make sure you put times against them. So how did that help? What was the end result? One production line that I worked on, just for the mechanical tasks, 63 hours per year of mechanical maintenance tasks to maintain that line. After the review, 35 hours was the total. We nearly halved the amount of work planned on that production line. 78% of tasks we deleted completely. How can we delete so many tasks? For how many years has this plant been running? They've been doing 78% of tasks that have wasted their time because we don't know the failure profile. We don't have good history. It's random failure. It's not age-related failure. The thinking is completely wrong. So delete them. 11% new tasks. The right tasks. That's the critical thing. It's not just about cutting tasks. It's about making sure the task does the right thing. What about electrical? 182 hours before we started, 200 hours after. So we actually increased the amount of hours, even though we deleted 83% of tasks. Because the tasks that they were doing took a lot of time, but weren't very effective. Now we've done less tasks. They take more time to do the tasks, but we're confident that they'll give us a better result. So when we combine the two, or the whole lot for all of the production lines there, how did that look as an overall picture? 900 hours before we started the process, 600 hours after. So we cut the amount of work by the maintenance team by 30%. Deleted 40% of tasks, increased a new task by 27% and moved a few other bits and pieces around. Okay, so massive benefits, not only on cost, but also time. We've freed up 1/3 of the amount of work time that the maintenance team can do. Now we can get them involved in more proactive things like root cause analysis, better plans, making sure the stores are stocked better. The key findings were we moved things from calendar to hour. Out of the 7 production lines, they didn't all run 24 hours, 7 days a week. Some run 1 week, some run all the time. Do as much condition monitoring as is practical. Vibration analysis was a big one, which we started doing. We did oil analysis on some of the really critical gearboxes. We found that equipment was way overserved. We just did too much maintenance for no reason. The operator would go and grease a bearing. Later on the same day, the maintenance person would come and grease the same bearing. Too much duplication of tasks because it wasn't formally documented well. Not enough electrical tasks and not enough that did the right thing. So it's a huge amount of benefits you can see from there. All right, so that's a packing plant. A lot of you work in oil and gas. Like I showed you in the graphs, the results are really similar. It doesn't matter what industry you work in, the maintenance fundamentals are the same. So here's a subsea example. We want to optimize the strategy, focusing on the rig itself, have some more realistic planned maintenance. We want to do the things that actually add value. Exactly the same steps. What's the failure modes? What's the consequence? What's the risk? Remember the quote I said at the start. You can have a good strategy that assesses risk, involving the right people, making the right decisions. It doesn't have to be on critical things, you can do it on everything. Subsea engineers tasks, similar sort of profile here. Deleted 35% of tasks that they did. Modified 34%, so changed durations or changed a bit of detail. Added 13% new tasks, deleted 13% non-adding, non-value-adding ones. Pretty similar numbers to the last one. Overall, again, deleted huge amount of tasks, nearly half the tasks deleted, 33% modified, 13% new. Same findings, unnecessary overhauls, duplication of work, doing things that weren't done for the right purpose when they should have been done in other ways. Even though our maintenance management system, CMMS, said that we had to do a planned maintenance, they would then go and do predictive maintenance. Or if it says no maintenance is required, they wanted to feel comfortable and still went out and did tasks. So the strategy wasn't being followed even though it was there. Eliminated a huge amount of a huge amount of work that wasn't necessary. A more realistic plan of what tasks are needed. Add in the working, the man hours, the tasks performed. We've got a really good understanding of how we can plan, how we can schedule our work. Makes us more effective. So what's next? Where do you go from there? We understand we could teach our teams through better training the fundamentals of maintenance. Okay, I find that a lot of people within businesses don't understand the fundamentals of maintenance well. They haven't been trained on it. Get the training in place well. We know how to put a strategy together through ISO 55001 maybe, or through our teams. We can review criticality. Where do we go from there? What does the future hold for maintenance? Technology. Technology is going to help us massively. The Internet of Things, if you've not heard of the Internet of Things, for those of you who go for a run and you use an app to track how far you ran, how many calories you burnt, how fast you ran, that's using the Internet of Things. It's using a sensor in your phone to go to the internet to give you the data to help to determine how fast you were yesterday compared to today. We can use the same thing for predictive monitoring. Vibration analysis. What was the vibration yesterday? What's the vibration today? We can have remote sensors so we don't even have to fly out to a rig to do the testing. Connectivity is making things much more accessible and much easier. We can then use artificial intelligence to help predict when failures are occurring, to help simulate through digital twin what's going to happen. Collect the information, collect the data, build a model. It can be artificial intelligence or digital twin or just using our knowledge to make more advanced models. Gives us better confidence that we're going to have a failure at this point. Helps us plan it in better. Blockchain technology. If you've not heard of blockchain technology, most people think of Bitcoin. All blockchain technology is this. We're monitoring transactions that are visible. Every transaction that is made digitally gets tracked so that nobody else can change the records. That's all blockchain technology is in a very brief summary. Visibility, traceability of every transaction that's made digitally. Augmented reality, virtual reality, we can put goggles or glasses on to help us identify a piece of equipment, turn this valve, change this one. Here's a map of the floor. We can tell exactly where equipment is. Don't forget cybersecurity. How many times are companies going to get hacked before they decide to improve their security on their cyber? Data is what is important these days. We need to protect it. We need to make sure if we're using remote technologies and Internet of Things, we're protected. So now what? Now what would you do if you wanted to save money? If you want to improve safety, if you want to have your equipment more predictable, you want to reduce your stress, reduce your team's stress, and have a happier life, what would you do to be This person that I showed you at the start, this maintenance manager where they're reducing costs, more stable process, profits are up. I'm hoping that you've got a bit of an idea now as to how you would do this. How can you become this person? I asked you a question at the start. What are 3 steps that you gained out of today that you think would help you master your maintenance plan and reliability? So if you haven't written them down, I'm going to give you my 3 answers. First one is to set up the support that you need. We need to have the management support, the leadership, making the vision, setting the goals for the team. The support of the operators, total productive maintenance, providing that basic care, the condition monitoring stuff. Don't tell production this, but maintenance and engineering are there to support production. We are there to help make money, which is production. Okay, we use the advanced problem detection and solving skills, the techniques, the technology we understand, learning to support them. I'll deny it if you ever say that though. Do the right things, understand the fundamentals and the basics. What maintenance techniques have we got to choose from? Reactive, planned, predictive, reliability-centered maintenance, total productive maintenance, risk. And the third one, improve prevention as much as possible. Prevention and prediction. Only use the new technologies once you have number 1 and 2 in place. You could have the best technologies in the world. If you're not using the information, if you don't understand the decisions behind it, you're wasting your money and wasting your time. Most places are nowhere even close to number 3. Start at number 1 and 2 first to help get you there. If you want even better information, if you want some even better help, I do training through the Institution of Mechanical Engineers, and I've set up a program especially for your region, especially for your time zone. If you're in Northeast or Southeast Asia over there, the 2 ones to help you get the fundamentals right first. World-class maintenance, 12 hours of CPD, career professional development. We give certificates out and all that for your record keeping as well. I do them online at the moment because face-to-face isn't able, but I'm definitely hoping to get over there soon again and get back to doing the face-to-face. And the other one is if you're a little bit more advanced and you want to do reliability-centered maintenance as well. So I've got a link in the bottom there, imeche.org. Go to there for the training calendar. Nice early start for me at 5:30 in the morning over here. As I said, I live in Aberdeen in Scotland, but for your time, I've made it a bit more comfortable, 12:30 start in Malaysian time. And if you book both courses, you're actually going to get a pretty good discount for doing them one after the other. So some contact details there, inquiries at imeche.org. As I said, my name is Matthew Laskaj, Laskaj. I'm on Facebook, LinkedIn, all those places. So please feel free to connect with me, ask questions, contact me anytime you want for help. And I would love to see you on any of the courses. But more importantly, I would love to see anybody with any questions. So I'm going to throw it back to Yvette.
All right, thank you, Matthew. Thank you for that very, very interesting session. We see that many people have got questions for you, but before we go to those questions, we've got questions, lots of questions, but before we go to that, I'd like for viewers to please go up to the top of the screen after the session. Please go and fill up the feedback form. So that feedback form will help us to gauge what kind of courses or what kind of input what kind of webinars that you would like to hear from us, so that in future perhaps we can try to organize such sessions for you. So just a short information on that. So now let's go to the questions that we have. So we have one question from Jacqueline Lucas. Okay, so since effective maintenance is going to prolong the life of an equipment, does it not stand in the way of the user employing newer and better technologies? And I totally agree with this. What if you maintain your equipment so well that it potentially lasts forever? Then how do you justify getting newer stuff with more advanced technology? How do you do that? What are your thoughts?
The question has to come back to what is the purpose of you as a maintenance or engineer? What are you trying to achieve? Like you just said then, Yvette, you're trying to make sure the equipment lasts longer, or you know when it's going to fail, or you can predict when it's going to fail. So if you're happy that it's lasting long enough, we don't need to get new technologies. So don't even worry about new technologies and new things, because it's doing what you want it to do. You've just saved money. If you have a basic maintenance plan that does everything you want it to do, don't worry about technologies. It's doing what you want it to do.
But the idea of technology helps us to save money, right, in the long run?
Not always, no.
Not always? Well, okay,
no,
fine,
because
not always.
if I've got a piece of equipment, I've got a pump running, and it's doing exactly what I want it to do, why would I spend money on sticking a vibration and analysis tool on it? When it fails, is it cheaper to replace the pump, or is it cheaper to have constant vibration analysis monitoring on that pump throughout its life? It only fails every 10 years. How much does it cost me to monitor the vibration of that pump over 10 years versus changing the pump once in 10 years? So maybe the vibration analysis will prevent that failure or predict when it's going to happen, and it gives us a warning sign. So what you have to do is look at what is the reason for buying the technology.
Yes.
Does it make
justification
cheaper, safer, better? If not, don't buy it.
All right. We Malaysians love to save money, so I agree with you.
All right. Just save different money.
It's all about money, isn't it? All right. So thank you very
much. If you're not saving money, you go bankrupt.
We've got another question here from Pang Cafe. Would data analytics and machine learning help to analyze the data collected so as to better understand machine conditions?
Yeah, that's a great question, because we all love to collect information. Collecting information these days is so easy, isn't it? We can do it from all sorts of methods. But then what do you do with it? So there's two sort of extremes. Some people are collecting none. Some people are collecting far too much, and they collect so much they just don't know what to do with it. So what you've got to do is collect the information that will help you achieve your goal. Again, let's look at a pump. How many times has it failed in 10 years? What are the types of failures or failure modes that you have had? Does the same failure happen every time? Maybe it's the packing that fails after every 6 months. Collect what happens to the process throughout that 6 months that potentially could cause that to fail. Maybe you want to collect how often it's going to cost you. So machine learning will help you to an extent, but I find that most places aren't anywhere near the point of being able to use the machine learning because they're not as advanced in collecting the information in the first place, or they don't understand the failure modes and things. The places that it does help is, like you just said about with technologies, we can stick remote monitoring on things. So again, vibrational analysis. We could stick a probe on it that we have 24-hour-a-day monitoring of the vibration. We're then going to collect the data over every single second of its life, and then we can use the algorithms or whatever to say, oh, it's risen all of a sudden, now we're at an alarm level. So collect the information for helping root cause analysis or predicting when it's going to fail. If your consequence of failure is too high, that's when you need to start collecting better and doing it more in depth. Maybe use reliability-centered maintenance.
So at the end of the day, right now, we are all about machine learning. We're all about data analytics. We've got these words flying around, big data. So again, coming back to the previous question, in order for us to move forward and use big data, we must be able to have the facility to be able to collect it. And again, if we were to continue to maintain our instruments, our machines to the extent that it lasts forever, we might be getting in the way of advancing technology, even though we get to save money, isn't it?
Yeah, absolutely. So the first step is you have to start collecting it in the first place. A lot of places, they just don't have that history. So just collect the basics if you need to. Then establish a baseline. When you're confident that you've got enough information, then you can start using it to detect, is it, because maybe a pump runs at a high vibration level all the time. And if you start to do a check, oh, look, the vibration's high, we better change the pump out. Well, no, because maybe it always runs there. So you need to have a baseline, enough time to establish that, and now is it going up or is it going down, and then decide it.
That's where an engineer comes in. You need to really understand your machines. Yeah?
Yes.
Thank you.
Yes.
So now we've got another question. Okay, this is from Lai Naishan. Okay, there is a strong relationship between condition monitoring, predictive maintenance, and overall equipment effectiveness, OEE. Is this true, and what are your thoughts?
So OEE is a combination of monitoring your quality, your productivity, so time, and how many good parts you're producing and how much you're running for. So it's a good reliability measure or process reliability measure, and it gives you a number, a percentage. So if I'm making 90% quality parts and I'm making 87% time and I'm running for 65% something else, you multiply the three out and that gives you your OEE number. And it's a measure. But what are you measuring against? How do you know that that 67% is good or bad? So you could use best practices. You can use world-class numbers, which is what I go through in the world-class maintenance course. Or you could just say, what did I achieve last month? Can I get better? So that's a measure of where you're sitting now, or that shift, or that day, or that week. So it's a measure, that's a number of how you are performing in reliability. Predictive maintenance is only there to help predict when equipment will fail. So yes, by having better condition monitoring and better predictive maintenance, that will increase the uptime or the availability of your equipment. But it doesn't help your quality, and it doesn't help your other times. So it's one part of those three pieces. If you improve predictive maintenance, you improve reliability, you improve uptime, which by default you improve the amount of stuff you make. So it's one piece of helping OEE, but it's not the only part.
It is one very important piece.
Yes.
Because without it, nothing else will work very well. Yeah?
No, you're just going to have more breakdowns.
All right. We've got one more question. This is from Howard Young. To what extent, okay, this is showing that he was really paying attention to the graph from earlier, your poll. Yeah, so to what extent is the assumption tolerable in maintenance, especially in the case of graph F, where the possibility of failure is random?
Yeah, great question. And this is the thing for me where I find it when I'm doing these studies in groups. So I go into a lot of companies and I help them develop their maintenance plans and do training for teams and things. So if you're a company out there and you want some help and doing these trainings, absolutely can help you with that. The hardest part to get through for people is, let's say we've got a maintenance fitter and he or she has been doing maintenance for 30, 40, 50 years maybe. As a maintenance person, what we want to do is make sure our equipment is running well. We don't like to see leaks. We don't like to hear it making noises. I like to feel comfortable that I'm doing something to make it run better. And this is why a lot of the time we do planned maintenance, because I feel better if I'm doing maintenance. But if I don't know where that end of the graph is, where is that point where it's going to start to wear out? I could be doing my maintenance way too early, which means I'm wasting money, or I could be doing it way too late, which means it's going to fail before I do my planned maintenance. So unless I know where that dotted line was, where that wear out part is, how do I know when I'm doing the maintenance is right? Again, think of a light bulb. Do we ever do planned maintenance on a light bulb? We shouldn't, because, as I said, I can turn on today and it works fine. I can turn on tomorrow and it might not work. Let's say I want to make sure it's going to work for the rest of the day. I'll go and test it. Turn it on, yep, it's working, turn it off. Half an hour later, turn it on, it's broken. Planned maintenance will not fix that because it's almost a random failure. We don't really know when it's going to fail, so why are we planning maintenance in? Instead, we're looking at that F profile. When we turn a light bulb on for the first time, maybe I dropped it before I installed it, maybe I didn't screw it in right. There's a a bit more of a chance it fails the first time than a week later. So if I can do less changeovers, I need a backup plan for when it does fail. We know it will fail at some point. It doesn't really matter when, because what happens when it fails? I go to my cupboard and I change it with the new one because I've got a spare part. If it happens at night time, no problem, I'll turn my hall light on. I'll turn my torch on. I have a plan when it's going to fail. The consequence isn't much. So if it's a random failure, those last three, don't plan maintenance in because you're wasting your time. If it's one of the first three graphs, then absolutely planned maintenance is good. But remember, it was only 11% of the time. What percentage of planned maintenance in your plant is planned maintenance? I'm going to bet you it's way more than 11%.
Okay, so that's interesting, knowing when to do your failure analysis. So another question which is very related to what you just mentioned. So what about knowing how to identify it? So ways to identify failure profiles when you are limited with limited historical data. How would you do
Excellent
it? How would you
question.
suggest?
Yes. And this is what I said, a lot of places don't have enough information to base it on. So, as you just said, great question. How do you do a maintenance plan? We need to involve the right people. So, as I said, when I do my reviews with maintenance plans, yes, we've got to do a whole lot of work up front. So we've got to get as much history as we can. Sit in a room with the right people. So the operator and the maintenance person has a massive amount of knowledge of how that behaves. I can go and walk around and walk and ask the fitter or operator and say, see that pump there, it's making a noise. How long does that make a noise for before it actually fails? It always does that. It can go for 2 months like that before we need to change it out. Well, there's your history right there. I have 2 months from the time it makes a noise to the time I need to change it out. Or a lot of equipment's got really good information from the manufacturer, especially things like bearings and pumps and those sorts of things. They do a massive amount of testing. Go to the original equipment manufacturer and ask them to provide you with some history for their equipment, and that's a really good starting point. Then as you build up your history, you can modify it a bit after that. So operations and maintenance teams on the floor and manufacturers would be my starting point if you don't have enough information.
Thank you for that. We've got 2 more questions, maybe a quick run through the 2 questions before we wrap up for the day. Yeah? So regarding mechanical software packages, what would you recommend to predict condition of equipment? We've got a question from Rahman Ashina here.
All right, so there's kind of two bits to that. Is if you're looking at software to predict the condition of an equipment, you need to look at what predictive equipment you're using in the first place, and it will come with that software. So say vibration analysis was your thing and you wanted to make sure that your pumps and bearings and things and motors weren't vibrating, you would need to speak to somebody who provides the equipment. What does that hook back up to? And they will talk about what sort of software that you need for that specific thing. A lot of companies will have what we call a CMMS, Computerized Maintenance Management System, and that's what they use to plan and schedule and keep all their history information in there. So things like SAP, SAP, Oracle, Maisie, there's a whole range of different ones, and most places these days have those in place. I find that just as a starting point, keep it in Excel. It gets a bit hard and a bit awkward after a while to manage it, but if you're starting with zero, just collect it. But if you're using technology to collect it, it will usually have whatever that manufacturer has, so I would ask them.
Right, thank you so much. Okay, one last question before we end for the day. This is about the curve that you showed earlier, about the infant mortality curve. So is it due to a design issue or a quality issue? How is it related to reliability or maintenance?
Yeah, great pickup there. So the infant mortality graph says there's a higher chance of failure at the start, and then it sort of fairly quickly evens off to random throughout its life. That's what that kind of curve tells us. So what are all of the ways that it can fail day 1 or day 2 when you start it up? Yes, we could have designed it poorly. We could have transported it badly and we could have dropped it. We could have stored it in a room that wasn't, if it was electrical, it could have been humid and could have got wet and rust. It could have not been protected well. The operator could have installed it wrong. The operator could have started it up wrong. There's a massive list of things that could cause us to first time fail. So that helps us make sure our process is in place for that startup process. But by understanding the graph, as a reliability or maintenance or an engineer person, it makes me think every time I say we need to do maintenance, do we really need to do maintenance? Because if we don't, we're going back to the start of that graph. And now we're going back to the higher probability. So as a reliability person, the way that graph helps me is to actually make me think better. Do I really need to do this task? Does it help me reduce the consequence, reduce the risk, prevent the failure? If not, redesign it or just let it run to failure. Don't even touch it at all, because like the light bulb, touch it and you're probably going to blow it. Leave it, have a way to fail. So that's how I use that.
Okay, thank you so much. You know what? The topic is so interesting that we've got more questions, but unfortunately, I think we've run out of time. So if you've got more questions for Matthew, please keep them coming. Do not limit yourselves. He's very happy to field all your questions. So please leave them in the comments, and perhaps Matthew can get back to it after the session. Yeah?
Yeah, absolutely. And
if
you connect on the Facebook and LinkedIn as well, you can catch me that way. Join in. I said my name's pretty easy to find. There's no other Matthew Laskaj in the entire world, so you won't have trouble in finding that. But I said the programs we've got set up in place in July just for your areas. So get in touch if you want one in company or yourself as well. I'd love to see you at those.
All right. So if you do want to get information on these events, or if you want a specific topic that you would like Matthew to present on, please fill up the feedback form. The link is right at the top of the screen. Fill it up, and you will get the information about it if and when it is organized. So thank you very much for joining us today, Matthew.
Thank you for having me. It's been awesome.
Yeah, okay, so hopefully you can have another session with us once our viewers get back to us on what they want to hear about.
Absolutely. That'd be great.
Right, so thank you very much.
Thank you everyone for joining.
Thank you very much. Thank you and have a good day. Goodbye.
Thank you. Bye.